Welcome back to Honors Calculus. In this video, we'll be starting into Lesson 2 on the coordinate plane with a discussion of the equations of lines. In your previous mathematics courses, you've probably come across two distinct different definitions of a line. A line is the shortest path connecting two points, and a line is the graph of an equation in a certain form. Today we want to take a closer look at that and show how and why those two ideas of lines are in fact the same thing. With that, we'll be able to build up the tools that we need in order to write the equations of lines, which is going to be a very useful tool, a useful skill for us as we move forward in this class. So without further ado, let me get my head out of the way and let's jump in. Starting off with some things you're very familiar with. The rectangular coordinate system with a rectangular coordinate plane is the two-dimensional structure formed by two real lines, which we call the x-axis and the y-axis. By convention, we draw the x-axis horizontally, the y-axis vertically. We define the angle between these two axes to be a right angle. If you draw them differently, we still define it as a right angle, and it really makes some weird things happen in geometry. So let's be careful to draw them in what we usually refer to as a right angle. The point where the two axes cross each other is called the origin. And any point on the coordinate plane is described by an ordered pair x, y. Given that x and y are both real numbers, and you need two of them in order to describe an ordered pair, we can define the set of all points on the coordinate plane as the real numbers squared. So that's the set of all xy such that x and y are both real numbers. Right, so r squared is the set of points on the coordinate plane. Right. Up next, a little bit of vocabulary. Again, all things that you are accustomed to, but I want to be careful and make sure that we can distinguish between these ideas because in a lot of algebra classes, you don't pay close attention to the difference because it is subtle. Right. A conditional equation in two variables is any equation which contains an x and a y. And a solution to a conditional equation A solution to a conditional equation is an ordered pair x comma y which satisfies the equation. The graph of a conditional equation is the set of all solutions. And finally, we can visualize a graph by plotting it on the coordinate plane. So the graph is the set of all points. Plotting the points is taking each of those points in the graph and placing them somewhere on the plane. Graphing the equation is finding the set of solutions and using the visualization to represent it. Let's try that again with characters that actually look like the letters of the English alphabet. A first-degree equation is any equation which can be written in the form ax plus by plus c equals 0. If the equation can be written in this form, then for a different value of c, you could also write it as ax plus b equals c. You can also rearrange solving for x, solving for y. There are several other forms of a first-degree equation, many of which you are already familiar with. But we end here by defining that a line is the graph of a first-degree equation. For our purposes in this course, that is the definition of a line. As I said in my opener, I am certain that everyone taking this course has previously needed to graph a line by being given a first-order equation, sometimes called a linear equation, and rearranging it in some way to find some sort of key piece of information in order to sketch the graph. But I am also sure that everyone taking this course has been taught that a line is defined as the connection between two points. And so we want to get there. We need to get there from here. And that's my big theorem for today. All right, this theorem is called the point-slope form of a line. Again, something that you may be familiar with from previous mathematics courses. Let's let x naught, y naught, and x1, y1 be two distinct points. And to drive home that they are distinct points, I'm going to further insist that x naught and x1 are not the same. Sharp-eyed among you might notice that if I insist that x naught and x1 are not the same, then trying to draw a line through these points will ensure that the line I draw is not a vertical line. We'll take a look at the case of a vertical line as a separate theorem. The theorem claims that there is exactly one line which passes through these points, and the equation of this line is y minus y naught equals m times x minus x naught, where m, which is defined as y1 minus y naught over x1 minus x naught, is the slope of the line. All right. So we've stuck a definition in here, the slope of a line. And in the context that we are going to be looking at things, in the context of calculus, slope is simply defined to be a convenient shorthand for point-slope form of a line. That is the only meaning that we are going to give slope in this course, except that it turns out that understanding this idea of slope is going to be fundamental to most of what we do in the course. But the proof here is honestly fairly straightforward, although not exactly easy. We are simply going to assume that there is at least one line that both of these points satisfy, at least one line that both of these points happen to fall on. And by making that assumption, we are going to show that we can go through the derivation and find that that line must have the equation that we just wrote down, thus guaranteeing that the line is unique, because by making no other assumptions, we have a specific values, well, as specific as you can get for these x naught, y naught, x1, and y1. Without loss of generality, WLOG, another one of those Woolog statements. Without loss of generality, I can assume that b is equal to 1. There's no real value in assuming that b is equal to 1, except that it does limit what I am able to do. And limiting is a good thing here, because for any value of b, I can multiply both sides of this equation by b. It'll give me a different value of a and a different value of c, but it won't change the equation. Or another way to think of that, if I had this equation set up where b was not 1, right? Let's say I had 5x plus 2y plus 7 equals 0. I could divide both sides of this equation by 2, which would give me 5 halves x plus y plus 7 halves equals 0. These two equations are equivalent. And because of that, they are the same equation. They have the same graph that defines the same line. So that's what I'm talking about here when I say without loss of generality, we can assume that b is equal to 1. If we assumed that b was anything else, we could just divide both sides of the equation by that anything else and get an equivalent form of the equation where b was equal to 1. But narrowing this down and having only 2 parameters in the equation instead of 3 is definitely going to make my life easier. Now that I have that, because these 2 points both satisfy the equation, that means I can plug each of those points into the equation in turn. Ax naught plus y naught plus c is equal to 0, and ax1 plus y1 plus c is equal to 0. I now have a system of 2 equations in 2 unknowns. And as you have certainly seen in an algebra course at some point in the past, when you have a system of 2 equations with 2 unknowns, you will be able to find the solution to that system. The first thing I'm going to do in that process of solving is use the transitive property of equality to say that each of these left-hand sides is equal to 0. And if 2 things are each equal to the same thing, then they must be equal to each other, giving me ax naught plus y naught plus c is equal to ax1 plus y1 plus c. All right. Subtract c from both sides of the equation. And shuffle things around so that all of my terms with a are on one side, all of my terms without a are on the other. Factor out that common factor of a. And we get that a is y1 minus y0 over x0 minus x1. Well, that's almost what we were looking for, but not quite. So let's fix that not quite by noticing that if you switch the order of subtraction, it takes the opposite of the expression. So if I switch the order of subtraction in the denominator here, I'll get the opposite of y1 minus y0 over x1 minus x0. And that fraction, y1 minus y0 over x1 minus x0, is exactly the thing that we called m in the setup of this theorem. So we have a negative in front, which stays in front. We have a fraction, which we called m. We get that a is the opposite of m. Plugging that in now, my equation is now negative m times x plus y plus c is equal to 0. All I need to do now is solve for c. There are a couple of ways I could solve for c. I think that the easiest is to plug in x0 and y0. Right? So c is m times x0 minus y0. And if I take that value of c and I plug it back into the general form one last time, I've got what I need. All that's left is to do a little bit of rearranging. Move all of the x, or all the terms that have an m onto the right-hand side. Factor out that factor of m. And we get that point slope form, y minus y0 is m times the quantity x minus x0. And that is, in fact, all we need to do for this proof. We assumed that we had a line that passed through both of these points. We went through and did some work and found that that line must be the graph of the equation y minus y0 equals m times x minus x0. That, first of all, verifies that the line exists because we know what y0, m, and x0 are based on the given information. And second of all, ensures that the line is unique because I made no assumptions about the line. I just said we had a line and this fell out. If you're following along in the prepared notes, you will notice that the next thing is a theorem that takes another page of notes showing you how we get the vertical line if we had 2 points x0, y0, and x1, y1, where x0 and x1 happen to be the same. You would get an equation in the form x equals x0. That's not really something that we're going to make much use of, so I'm not going to go through the derivation, but I did want to mention that that is something that shows up in the typed out notes. Instead, I'm going to jump into an example And let's write the equation of the line which passes through the point 3, 7 and has a slope of 2/5. What we know about lines is that every line is defined based on y minus y naught equals m times x minus x naught. And we know that we have a point here, which gives us the value of x naught and y naught. We have the slope given, that's the value of m. All we have to do is substitute these things in. So y minus 7 is 2/5 times the quantity x minus 3. Technically speaking, that satisfies the problem. We were told to write the equation of the line, and we have written the equation of the line. But in practice, we know that writing an equation in this form is not very useful, so we'll take the time to simplify the equation and try to get it into a form that is more useful to us. Specifically here, that's going to mean solving for y. So let's distribute on the right-hand side. Right, 2/5 times x is 2/5 x, 2/5 times 3 is 6/5. And then if I add 7 to both sides of the equation, I have 6/5 plus 7, negative 6/5 plus 7. 7 times 5 is 35. So 7 is the same thing as 35/5. And now I can add negative 6 plus 35 is 29. So I get that y is 2/5 x plus 29/5. All right. One last thing about points on the plane before we move onward. And that is the distance formula. The distance between 2 points, x2 minus x1 squared plus y2 minus y1 squared. Take the square root of all of that. And we are taking the approach in this course, just like we did in the real line, defining distance in terms of absolute value. We define distance in the plane in terms of this expression. And chances are good when you were first introduced to the distance formula, it was shown to be correct in terms of the Pythagorean theorem. We actually take the opposite approach in this course. We start by defining the distance formula, and we can use that to prove the Pythagorean theorem by proving that if you put the coordinate axes right here, then this is the point B0, this is the point 0A, and then C is the distance between them. So a fairly straightforward proof based on our definition of the distance formula. But the real important thing in this course is, or in this lesson, is writing the equation of lines. So I want to leave you with one to try on your own. I would like you to write the equation of a line whose slope is 7/3 and which goes through the point -2, 5. Hopefully this is something that you have worked through in the past, but you've seen an example now. So take the time to write out your solution here to submit, and I'll see you in the next video.